Good morning, everyone. Welcome back. Thank you for joining us. We are glad that you're here. I'm Steve.
And I'm Scott.
And together we're Backyard Musing Science and Technology channel.
Yeah, and today we are talking about a very interesting topic, as we usually do, but this one has to do with a source of water underneath a source of water that is not very useful other than for a few things. And this is kind of interesting.
Scientists found extensive fresh water beneath the Great Salt Lake, offering new insights into groundwater flow and potential environmental solutions. A new study is shedding light on what could be a vast underground freshwater reservoir beneath the Great Salt Lake. Researchers used airborne electromagnetic, called AEM, surveys to image geologic structures below Farmington Bay and Antelope Island along the lake's southeastern shore. Would you like to know more?
Yeah, and this is fascinating because I'm thinking when I first saw this, I thought, what about our Salton Sea? I wonder if there's a underwater freshwater source there. So anyway, geophysicists at the University of Utah analyzed the data and found that freshwater saturates sediments beneath the lake's highly salty surface at depths of about 3 to 4 kilometers, which is about almost 2 to 2.5 miles, or 10,000 to 13,000 feet. That's pretty deep. Yeah. The helicopter-based survey followed earlier observations of freshwater rising under pressure at several locations on the exposed lake bed in Farmington Bay, forming unusual mounds covered in dense phragmites. Is that what that is? Phragmite reeds. Interesting.
Yeah, very interesting. According to lead author Michael Zdanoff, the study is the first to show that AEM methods can detect freshwater beneath the thin, conductive saltwater layer at the lake's surface. His team also mapped how far the freshwater extends beneath Farmington Bay and estimated the depth of water-saturated sediments by identifying the underlying basement structure.
The findings were published in the Nature-affiliated journal Scientific Reports on February 27th of this year. The work is part of the broader project led by the University of Utah's Department of Geology and Geophysics and supported by the Utah Department of Natural Resources to better understand groundwater beneath the Great Salt Lake, the largest terminal lake in the Western Hemisphere. Led by senior faculty and graduate students, the project has already produced 2 additional papers with more expected.
Wow.
Yeah.
The results suggest that freshwater is moving into the subsurface toward the lake's interior rather than entering from the edges, which is what scientists would typically expect, according to hydrologist Bill Johnson, a co-author on the studies.
This is a quote. The unexpected part of this was that the salt lens that we see near the surface across the playa, it's that the freshwater underneath it extends so far in towards the interior of the lake and possibly under the entire lake. Wow, that's because that's a big lake.
Yeah.
We don't know, said Johnson on a recent appearance on KPCW's Cool Science radio show. Never heard of that one. Going on with the quote, what we would normally expect as hydrologists is that the brine would occupy the entire volume underneath the lake. It's denser than the freshwater. You'd expect the freshwater from the mountains to come in somewhere at the periphery, but we find it's coming in towards the interior, maybe like a spring or something. I don't know. And that's what appears to be deep volume of this fresh water coming in underneath the saline's lens.
I wonder if this brine is acting as, for lack of better words, a magnet to attract that water, H2O, and pull it up from so deep,
Yeah, I don't know. I wonder if they're going to try and
conductivity. I mean, a battery's got a liquid salty. I don't know. All right. Interest in the phenomena grew after circular mounds began appearing on the dry lake bed recently. Each mound measures 164 to 328 feet across and is covered with reeds up to 15 feet tall. Falling water levels have exposed around 800 square miles of lake bed. now a significant source of dust pollution affecting nearby communities in Utah.
Yeah. Johnson, a professor of geology and geophysics, is exploring whether this artisan groundwater could be used to reduce dust emissions that contain toxic metals. Johnson and colleagues, including Mike Thorne and Kip Solomon, are seeking funding to expand the lake, expand the research across a larger area of the lake. So yeah,
Give me
I don't know.
more money.
Yeah, send me your money. But that lake, and then south of there, about 40 or 50 miles, is Utah Lake, and it is it's a freshwater lake, but it's not very clean. And they have what they call an inversion layer there. And I think we've even talked about that. It's been a while, but we talked about that inversion that they get. It's like a lake effect smog, and it affects the valley. I mean, it's pretty bad. I wonder if that's similar to what they're talking about here.
Oh, if it's dust, then that can get into lungs and stuff, really mess it up.
Yeah, absolutely.
Wow. The study measured electrical resistivity down to about 100 meters using airborne electromagnetic surveys to distinguish freshwater from more conductive brine. To carry out the work, Johnson and Zdanov hired a Canadian geophysical team to fly equipment suspended beneath a helicopter in February 2025. The aircraft completed 10 east-to-west survey lines across Farmington Bay and the northern part of Antelope Island, covering 154 miles.
I wonder why they had to go to Canada to do that. Find that team. Interesting. The data allowed researchers to map the boundary between saltwater and freshwater. One Phragmites mound, for example, sits above a location where freshwater rises through a break in the otherwise impermeable layer beneath the lake. I don't know.
Lead author Michael Zdanov's team at CEMI has developed a method for creating three-dimensional images of the subsurface by combining airborne electromagnetic data with magnetic measurements. In this study, the approach produced a detailed tomographic image extending deep beneath Farmington Bay, revealing key features of its geology and groundwater system.
Magnetic data show that the basement beneath the Farmington Bay playa is relatively shallow, less than 200 meters or about 656 feet deep, before dropping sharply to 3 to 4 kilometers, and that's what we talked about earlier, about 2 to 2.5 miles. This transition occurs beneath a Phragmites mound and marks a major structural boundary that warrants further study.
Although this initial study covered only a small portion of the lake, Zdanov believes similar airborne surveys could span the entire 1,500 square miles. A full survey could support regional water resource planning and help guide efforts to locate freshwater beneath terminal lakes around the world.
Yeah, there again, going back to Salton Sea. So
it said that the brine was conductive. And I remembered something in the construction industry. If we've got groundwater that's pretty high and we're supposed to be excavating down, we'll take rods around the perimeter, metal rods, and we'll hook a current to it, and that'll draw the water back to the rods so that we can excavate, inside. So I'm wondering if that conductivity was pulling that water up.
So when you do that, do you still have to shore? You still have to put shoring in?
Yeah.
So, but you're just drawing the majority of the water, right? It's still kind of muddy and
instead of a continuous pump, they're putting it at different locations and just moving the water out through conductivity.
Interesting. Yeah, I'm envisioning, let's tunnel down and find out what maybe there's like a cavern down there or something that's separating the salt bed from the fresh water.
Like an aquifer? Like an aquifer.
Exactly. So,
all right, folks. Thanks for joining us. We hope you enjoyed this.
Yeah, thanks for listening. Take care. We'll see you this afternoon.